Hello everyone, today we're talking about linear combinations and vector equations. This is material from 1.3. So today we'll see how this seemingly new concept of a linear combination is actually connected to the ideas of linear systems that we've been studying so far. And I want to start out maybe with an example that continues from last time. So let's consider the following question. Can the vector, let's say b is 7, 4, minus 3, can this be written as a linear combination of A1, let's say is 1 minus 2 minus 5, and let's say A2 is 2, 5, 6. Okay, so that's a question I can ask. Now let's unravel that definition a little bit. So what does it mean to be a linear combination? So what I'm really saying here is that, i.e., we want to find weights, which are just real numbers, x1 and x2, that satisfy, make the following work. We want to take 7, 4, 3 equals whatever that weight should be times the vector a1 plus x2 times the vector a2. So, again, this is what it means to be a linear combination, is that there's some choice of weights. And let me just emphasize that x1 and x2 are, what we think of as the unknown. So these are the things that we're trying to find. If we can find these weights that work, then yes, the answer is yes to that question. We can write this vector as a linear combination. Now, let me just say that this has a name. This is called the vector equation, or a vector equation. Because, it's an equation because there's unknown things here. There's unknown weights that I'm trying to find. It's a vector equation because there's vectors involved. Okay, so how would we actually try to solve such a thing? So what I'm going to do is just unravel the definitions. 7, 4, 3, I want to write as this thing. But what is this? So this is, the sum of two scaled vectors. How do I scale x1 times this vector? I take x1 times each coordinate, right? Plus x2 times that vector, which is 2x2, 5x2, 6x2. Remember, that's how we scale vectors coordinate-wise. And then let me go, a step further. I'm going to say, how do I add vectors? Well, remember, similarly, if I want to add two vectors, I'm going to look at their coordinates, add each one. So this will be x1 plus 2x2 is the first coordinate, minus 2x1 plus 5x2 is the second coordinate, minus 5x1 plus 6x2 is the third coordinate. So now what I see is that what I want is that this vector equals this vector. In other words, if the vectors are the same, the first entry should be the same, the second should be the same, third should be the same. In other words, x1 plus 2x2 should equal 7, right? The first coordinate should be the same. Minus 2x1 plus 5x2 should equal 4. Minus 5x1 plus 6x2 should equal 3. And now we're in business. This should be kind of an aha moment because this thing is what we know and love. This is a system of linear equations. So what is this? This is a, so it's a 3 by 2 system of linear equations. And I'm putting an exclamation mark there because that's a nice insight that now we can reduce this thing to something we already know. Let me just emphasize that, as usual, when you guys see a system, you should be thinking about what the augmented matrix is. And you know how to get this. I just take those coefficients on the right-hand side to make a matrix. Okay? And let me just point out that I could have actually jumped straight to this. In the future, we're going to just jump straight to this system, this augmented matrix, because notice that I was asking to write, oh, by the way, there should be a minus 3. I think I forgot all along here. It's 7, 4, minus 3 is the vector b, and so now it is minus 3. But if I go back to this augmented matrix, notice that this is just the vector b that I'm shooting for, right? This is the vector that I want to write as a linear combination. And then A1 and A2 show up in the coefficient matrix here, right? So this is A1 and A2. They form the columns of the left-hand side of the matrix. And, so let's actually solve this guy, solve this system. Hopefully that's something you naturally want to see. So let me see if I can put this on the same page. To solve this system, we do the usual thing, we row reduce. So let me actually write the matrix here so I don't have to try to put both pages on one. So this was minus 2, 5, 4, minus 5, 6, 3. So what do? I'm going to go a little bit quick here. So here's my first pivot. I want to clear below it. I leave that first row alone. To clear below it, I add 2 times the first equation to the second. I get 2 times 2 is 4, plus 5 is 9. 2 times 7 is 14, plus 4. To clear the third row, I want to take 5 times the first equation, or first row, add it to the third. So this is 0, 16, and again, I missed my minus 3. There should be a minus 3 here. So when I take 5 times 7, it's 35, plus a minus 3 is a 32. Okay, so again, I missed that minus 3. But it is there now, and this gives me this matrix. What I'll do now is scale, I guess I'll scale row 2 by 1/9. This gives me 0, 1, 2. I'll scale row 3 by 1/16. This gives me 0, 1, 2. And now I'll clear below this entry. So I leave row 1 and row 2 alone, and I get 0, 0, 0. Okay, so at this point, what I can tell is that, here's my echelon form. So at this point, I can tell whether this thing has a solution. Now notice you have a 0, 0 here, but since this is a 0 also on the right-hand side, we're okay. There's no 0, 0, 5 row. So this indeed has a solution. The system is consistent. And in fact, how many solutions do we have? Well, there's a pivot in every column in the coefficients. So there's a unique, just one solution. I know that because there's no free variables. Okay? Now, what is that solution? Well, let's keep row reducing. So if I want to go reduced echelon, I'm going to take my usual clearing above pivot. So I'll clear above that one here. Clearing above. I take minus 2 times that second row, add it to the first. I get 1, 0, and then it looks like 3. So this is telling me that the solution, the unique solution is, well, x1 equals 3, x2 equals 2. This was x1, this was x2. Okay, great. That's the solution of the system. What we were actually trying to solve, though, was this vector equation, right? So let's see if it works. So I claim that these weights here, so we were trying to solve 7, 4 minus 3 equals x1 times this vector plus x2 times 2, 5, 6. Let's actually look at those weights and see if it works, right? This is something you can always check. So indeed, if I take 3 times 1 minus 2, 5, this was the x1, plus 2 times 2, 5, 6, I get a new vector. The first entry is going to be 3 plus 4 is 7. This will be minus 6 plus 10 is 4. Last entry is minus 15 plus 12, which is minus 3, and that's right. That's what I wanted. Okay, so it does work. I mean, that's the, if you believe what I did, that should be expected, but just to double check everything. Okay, so what's the punchline here? I want to just end with the sort of observation that we've more or less made, is the following. Let's get my notes for the language here. Okay, so the fact now that we've observed is that if you give me a vector equation, let's say x1 times a1 plus x2 times a2, I want this to equal b. This has the same solution set as the linear system that has augmented matrix so what was the augmented matrix? Remember, I took the vectors a1, a2, and I put them in the kind of left-hand side, in the coefficient side, and then I augment that with b. Okay? And so, again, this is just a translation of what we just saw. Let me go back to my picture here. So remember, I'm trying, in this example, I was trying to write this vector as a linear combination of these two. I just encode that in this system where the right-hand side becomes the vector I'm trying to write as a linear combination, and the left-hand side are the vectors that I'm using. And that's what I'm saying here in general. So in particular, B can be written as a linear combination of A1 through AN if and only if the system, this system where I've put those into columns and augmented it with B, if and only if this is consistent. Okay? And I think I'll stop there. We're going to continue next time with kind of digging deeper into this connection and maybe some more examples. So we'll see you then.